P2, whereas the pressure on the top surface is now less than the free stream pressure, right? So we can say that P2, the pressure on top of this surface is less than the free stream pressure. Okay, P2 is less than P1, right? So what happened next? Basically at the trailing edge. So just now we are talking about what happened at the leading edge on the top surface, and then now we are going to focus what happened when the flow continues. This is the trailing edge at the back here. So the flow must return to approximately but not precisely the free stream direction. Okay. So over here the flow is turned back into itself, and consequently a shock wave occurs at the trailing edge. So basically once the flow passes through the leading edge, it creates an expansion wave, but eventually it will then go into the direction of the free stream direction, the same pathway here. But once it reaches the trailing edge, okay, another shock wave occurs at that particular moment. All right, so that's what being happening there. Try to visualize the flow of the across this flat plate at an angle. And then we look at the bottom surface. Just now, earlier we looked at the top surface. Now we want to look at what happened at the bottom surface, right? So on the bottom surface, the flow is turned into itself, and oblique shock wave occurs at the leading edge. So basically at the leading edge, on the top surface, expansion wave occurs, but on the bottom surface, this is the oblique shock wave that occurs. Similarly, what happened on the trailing edge of the top surface. So there's on the bottom surface, the flow will experience an oblique shock wave, and the pressure on the bottom surface, P3, okay, we call it as a P3, which is actually greater than P1, the free stream pressure. So compared to the top surface where P2 is less than P1, but for pressure at the bottom surface, P3, it is greater than P1, and that's what happened when the flow across the flat surface at an angle at supersonic flow. All right. So and then following through at the trailing edge. So now we are looking at the flow going down here. It experienced the oblique shock wave where P3 is more than P1, and then reaching the trailing edge, the flow is turned into approximately but not precisely the free stream direction. Again, it tries to go into the direction of the free stream, right? And if we are looking at this figure, note that the top and bottom surface of the flat plate experience uniform pressure distribution of P2 and P3. So you can see that the arrows over there showing that there is a uniform pressure distribution from the leading edge to the trailing edge on the top surface. Similarly, on the bottom surface, we have the arrow in the opposite direction, P3, which is distributed uniformly, where P3 is more than P1. Okay, so as we can see here, okay, where what happened is basically we know that P3 is greater than P2 because P1 is in between. So P3 definitely is more than P2. So what actually happened over there, which this scenario will create a net pressure imbalance that generate, because P3 is greater than P2, obviously the pressure down here is greater, and it generates the resultant aerodynamic force. Aerodynamic force over here pointing away from the top surface, okay, which is called R, right? And indeed, for a unit span, the resultant force and its component, which is the lift and the drag, okay, per unit span can be written as follows. So the aerodynamic force R, the lift, as well as the drag can be written by the following expression. So basically, what happened in equations 2 and 3, that what we have already shown earlier, where P3 is calculated. P3 is calculated from oblique shock properties from chapter 3.2, and P2, the pressure at region 2, is calculated from expansion wave properties, chapter 3.6. So basically, we are now looking at the two scenarios where the flow experience oblique shock, okay, where we can see that because oblique shock happening down here, expansion wave happening up here. So when you want to find the properties of P3, you use the oblique shock properties, and then you want to find the properties for P2, you then use the expansion wave, the Prandtl-Meyer appendix. So the formulas that we have already looked at chapter 3.6. And moreover, so these are exact calculations and no approximations have been made, and we know already the inviscid supersonic flow over a flat plate at an angle of attack normally being given a value over there. Alpha is exactly given by the combination of shock or oblique shock as well as expansion wave that is being sketched over here. All right. So what we can see here, the flat plate case given just now is the simplest example of a general technique called shock expansion theory. See, it is a combination of the shock wave, oblique shock, on underneath the bottom surface at the leading edge of the flat plate, and the expansion wave happening on the top surface at the leading edge. So we call it as the shock expansion theory. So whenever we have a body made up of a straight line segments and the deflection angles are small enough, so that no detached shock wave occur, so the flow over the body goes through a series of distinct oblique shock as well as the expansion waves. And the pressure distribution on the surface, hence the lift and drag, can be obtained because we know already on the top surface there will be a uniformly distributed pressure, as well as the bottom surface we have a uniformly distributed pressure. Normally we call it as P3, and we can obtain the aerodynamic force R, where we have the components of lift and drag, okay, which can be obtained exactly from both the shock and expansion wave theory, which discussed in this particular chapter. So we will later look into an example to look into the scenario or the theory that we have already discussed just now. Another example of the application of shock expansion theory. So just now we look at just a flat plate traveling at a supersonic speed at an angle alpha. So now I want you to consider a diamond-shaped airfoil. So we have a diamond-shaped airfoil, and normally we call it as a diamond wedge airfoil at zero angle of attack in a supersonic flow, right? So compared to the flat plate just now, it is at an angle alpha, but for the diamond wedge airfoil, we consider the shape to travel at angle of attack of zero. So that's why we can see that the free stream flow, it is coincide to the front or the leading edge of the diamond wedge model over here. So assume the airfoil is at 0-degree angle. That is there's no value of alpha over there. So the supersonic flow over the airfoil is first compressed. It is first compressed, and then deflected through at an angle, we call it as eta, E over there, by the oblique shock wave at the leading edge. So we can see here, if we zoom in over there, we have a symbol E over there for top and bottom, because it is a diamond wedge, it is the same angle over there. Right, so what happened actually when the flow follow through the shape of the diamond wedge at the mid-chord. This is where the mid-chord happened. This is the mid-chord position. The flow is expanded through at an angle of 2 eta, 2e over there, right? Creating an expansion wave. So, of course, the first one you see the oblique shock wave, and then it is being expanded. There's an expansion wave in the mid-chord of the diamond wedge airfoil, right? And basically it's then turned back to the free stream direction through another oblique shock at the trailing edge. So basically it will experience an oblique shock, and then coming to the mid-chord, it experience an expansion wave, but eventually reaching the trailing edge, it will then experience another oblique shock, right? So you can see that that is what happened on the top surface. So looking at the pressure distributions on the front and back faces of the airfoil, which is sketched over here, and note that the pressures on face A, we have face A over here on top, and then we have face B also on the top surface, and then face C and D on the bottom surface, which is uniform. Uniform in terms of on the face A and the face C down here, okay, it is uniform and equal to P2 because it is at zero angle. So the flow going on top of the surface A and the flow going downwards across the face C over there will experience the same pressure value, right? P2, which is uniform, which is equal to P2. This is A and C is the same, right? And on faces B and D behind the diamond wedge airfoil, it is also uniform but equal to P3. P3 over there, and P3 also being experienced at down side over here on the D surface, right? And we also must take note that P3, right? P3 values are less than P2 values, okay? So in the leaf direction, perpendicular to the free stream, the pressure distributions on the top and bottom faces exactly cancel out. So basically whatever aerodynamic forces generated on the top surface, it is cancelled out by the opposite aerodynamic forces from the bottom that resulted to be no lift at all. L equal to 0. So in contrast, in the drag direction, so in the free stream direction, the pressure on the front faces A and C is basically larger. It is greater or larger than on the B and D. And basically this portion of the diamond wedge airfoil having a large drag compared to the behind the diamond wedge, and this results in a finite drag. So to calculate this drag per unit span, we must consider the geometry of the diamond airfoil, where we call the length as L, and length of L of each face, and T is the airfoil thickness. T basically the thickness of the maximum mid-chord, right? So that is the T. So the length L for each faces, A, B, C, and D, having the same length L, right? So we can then find the value of the drag, D, by following through this expression, and we can simplify to the value of D equal to the difference between the pressure at 2 and 3 times the thickness, and we call it as the equation number 4. So basically, what happened over there? The equation number 4 that we have already found now is calculated from the oblique shock theory, right? And P3, right? P3 is obtained from expansion wave theory. So basically, the value of pressure in front over here, P2, is obtained from the oblique shock theory just because the flow experience oblique shock, and the P3 segment, okay, the pressure at region 3 now is found using the expansion wave because there is an expansion wave happening at that particular position. So moreover, so these pressures are the exact values for supersonic inviscid flow over the diamond airfoil. All right. So the results of this section illustrate a very important aspect of inviscid supersonic flow. We have to note that equation 3 and 4, equation 3 for the flat plate and equation 4 for the diamond airfoil predict a finite drag for these two-dimensional profiles. So we have already seen earlier, for the flat plate, we have already looked earlier where the flat plate, we have the drag can be denoted by this expression, okay, where there is a component of the angle of attack alpha, okay. However, for the diamond airfoil or diamond wedge airfoil, there is no component of the angle of attack alpha because there's the angle of attack is 0, so we can we have to use the thickness of the diamond wedge shape airfoil. So that is for two-dimensional profiles. So basically, this is indirect contrast to our results for two-dimensional bodies in a low-speed incompressible flow. So basically, if you look at the aerodynamics 1 subject again, where the drag was theoretically 0, so that is in supersonic flow, the D'Alembert's paradox does not occur. So probably you want to revise back what do we mean by this D'Alembert's paradox. So I don't want to explain it again here because it's already been covered in the aerodynamics 1 topic. So basically, in a supersonic inviscid flow, so the drag per unit span on a two-dimensional body is finite. So this new source of drag is called the wave drag. Okay. So, and it's represent a serious consideration in design of all supersonic airfoil, namely, you name it, whether it is a flat plate or it is a diamond wedge shaped airfoil. So the existence of a wave drag is inherently related to the increase in entropy and consequently to the loss of total pressure across the oblique shock waves created by the airfoil. So when you look into a scenario, you have to determine whether the at the leading edge, whether it's going to have an oblique shock or it is an expansion a wave, or what happens. So basically that will determine whether you are going to use to find the value of P2 and P3 respectively using the appropriate formulas. All right. Let us now look into an example, example 4.1, based on what we have already looked into the theory earlier. For the past 20 minutes, we have already looked at the theory of a flow on a flat plate as well as flow on a diamond wedge airfoil. All right. So let us try to apply it on a problem over here. So basically, we want to calculate the lift and drag coefficient, so the CL and CD for a flat plate. So we have a flat plate similar to the examples earlier, right? So, and the angle of attack, alpha, is given as 5 degrees, and the free stream Mach number is given as 3, which is more than 1 over there. So immediately when we see this, we know already at the leading edge, I just want to repeat again, at the leading edge on the top surface, there will be an expansion wave, right? On the bottom surface, there will be an oblique shock wave, right? So moving to the end of the flat plate, the expansion wave, then the flow will then experience another shock wave over there, right? Oblique shock wave at the trailing edge, right? And then for the bottom surface, from oblique shock wave, the flow will then eventually experience an expansion wave. So basically, when we look at the uniform pressure distribution P2, right, which is less than P1 on the bottom surface, the pressure at region 3, P3, is more than P1, and we can see that the aerodynamic forces are there, which has a component of lift and drag. So they want us to calculate the lift and drag coefficients. Okay, let us go through this example. All right. So if we refer to the given figure, right? So first you must calculate the ratio of pressure on the upper surface. From our earlier equation, right? If we refer back into chapter 3, you will find that the V2 equal to V1 plus theta, all right? So where theta in this case is equal to the angle of attack alpha. So now we look at the Prandtl Appendix C, right? So from Appendix C, probably is I do not have to go into Appendix C. Maybe later you can see into Appendix C in your reference, where if you find Mach number equal to 3, you will find out that the V value is equal to 49.76 degrees, right? So using this equation, right, you know already V1 equal to 49.76 degrees based on Appendix C at Mach number equal to 3. Then you add on with the angle of attack alpha, okay, which is now equal to theta over here, so which is 5 degrees. So 5 plus 49.76, you will then obtain 54.76 degrees. So using the same appendix, when you look at 54.76, you wouldn't find exactly 54.76. It's just use the value nearby and try to interpolate and get the corresponding value of the Mach number. And now you know already from Appendix C, using this value, you try to find what is the nearest value for V2, and then get the Mach number that is being interpolated to become 3.27. So then what happened? You use Appendix A. Appendix A to find the value of the pressure ratio. So at Mach number 3, okay, so you find the pressure ratio P01 over P1, you get the 36.73, and for Mach number, Mach M2, which is coming from the earlier M2 over here, using Appendix A, you then find P02 over P2, which equal to 55, all right? So since we know earlier P01 is equal to P02, where solving that, which resulted that we will get the value of pressure ratio of 2 to 1 to become 0.668. All right. So next, what you need to do is basically focusing on the bottom side and the bottom surface of the flat plate, and using the theta beta Mach number diagram. So as I said, this is the continuation of chapter 3, right? So we have already seen this particular diagram. So in this case, Mach number is equal to 3, as well as given theta, which is equal to 5 degrees. So you trace back from 3 over there, you stop there, where it coincides with the 5 degrees of theta. You then get the corresponding value of beta. Again, in this example, it is accurately shown you 23.1. If you provide a value of 24 or 25, even 23, without the decimal places is also acceptable. Of course, the accuracy will just be a little bit far away, but it's not that significant. So hence, you then find the value of Mn1, right, where we know already the beta value, and you will obtain the Mn1 to become 1.177. All right. Looking into Appendix B now, right? So if you look at Appendix B, because we are solving using the oblique shock theory, right? So Mn1 already obtained 1.177. We now look at Appendix B at 1.177 to the nearest entry, right? The pressure ratio is 1.458. This value you read from the table B, Appendix B. And then to find the CL, you go back to the equation 2 that we have already obtained earlier, right? And the lift coefficient is obtained by the CL is the lift coefficient, right? Where L over QS, and then you have this expression, and then put inside the values that we have already obtained earlier, where we have the pressure ratio P3 over P1. We also have the pressure ratio P2 over P1. This is for the top surface. This is for the bottom surface. And we have the alpha value, which is the angle of attack. Okay. And then for air value, for gamma is 1.4. The Mach number given is 3. Then you will get the corresponding coefficient of lift to become 0.125. So that is the value that we want to find in this particular example 4.1 for the case of the flat plate. All right. So I would like to suggest all of you to go through this example again and try to appreciate why we use Appendix B, why we use Appendix A earlier, and then why we use Appendix C. So that when you go through step by step, then you will realize as we the flow following through the flat plate on the top surface, it experienced an oblique shock. It experienced an expansion wave. So you have to use corresponding Appendix C. And then when we go into the oblique shock, we have to use Appendix B. So that's what happened here, where we want to find P3, we use Appendix B. Okay, now how about the CD? They want also the value of coefficient of drag. So looking at equation number 3, this is equation number 3 that we have already looked before. So we put down the value of CD, and we know already P3 over P1, we know P2 over P1. So we put down the numbers, and we then obtain CD value to become 0.011. Okay. So that is what we can find in terms of using the expansion wave theory as well as the oblique shock theory. However, a slightly simpler calculation for CD is basically to recognize from equation 2 and 3 or from the geometry of given figure that CD over CL is basically tangent of the alpha. So knowing that tangent of the alpha, which is 5 degree, so we will also get from the value of CL, you found already value of CL, looking at tangent 5 degree, and you will get the same value of CD, which is 0.011, right? Either way, you get the same answer, all right? Okay, before we have a short break, probably best to go into a comment on the lift and drag coefficient. So this is just one slide over here, so that before we go for our short break, if we look over here in terms of lift and drag coefficients, we want to reflect again on the results obtained in earlier example 3.6, and you want to refer back our oblique shock topic, okay, where the drag coefficient was calculated for a 15 degrees half angle wedge in a Mark 5 flow, right? So look at that example, and where we have already calculated the CD value, and now looking at the results obtained at just recent example, the example 4.1 that we have just gone through just now, where the lift and drag coefficient were calculated for a flat plate at an angle of 5 degrees angle of attack in the Mark 3 flow. So we note that to calculate this coefficient for the CD or the CL, we did not need to know the free stream pressure, free stream density, or the velocity. So you can see that from this example, we do not have to know the free stream pressure, the density or the velocity. All we needed to know was what shape of the body. Is it a flat plate, or is it a wedge diamond wedge airfoil? Okay, and more importantly, over here we also need to know the angle of attack and the alpha value, right, as well as the free stream Mach number. Okay, so for the examples in this chapter, we are dealing with in-visit flow, so the Reynolds number is not relevant, where we only look at the free stream Mach number and the alpha value, the angle of attack value. So with that, I believe it's best for us to stop for a while. Maybe there are questions would like to be highlighted by students, and we can entertain that first.